Our next topic of study is called the Doppler effect. You've definitely heard of the Doppler effect before, or at least experienced it before. You'll see what I mean in a minute. Before we get into what the Doppler effect is, let's talk about sound. So, sound, just like the speed of light, has a certain velocity or a certain speed at which it travels at STP, or at standard temperature and pressure in air. So, sound travels at 331 meters per second. On your reference table, it says 3.31 times 10 to the second meters per second. It's the same thing. This is just standard form. A lot of times when you're reading questions, they're going to talk about sound, and you'll have to either solve for the frequency or the wavelength, or depending on what the question asks you. They will not necessarily give you the speed, and that's because it's a constant. It's right on the front page of your reference table. So if you think you're missing speed, as long as it says that it's traveling at STP or traveling in air, 331 meters per second is the way to go. So sound travels more quickly through denser mediums. We talked about this last week. And when we said that you're able to put your ear against the door to eavesdrop on somebody in the outside of your room, or you're able to put your head on the ground and be able to hear earthquake tremors as rather than be able to hear it out in air, you can put your ear down on the floor and be able to hear people walking towards you. These other two here, seawater and steel, I put them on here, but in turn, just so that you can kind of get an understanding of the way that sound travels faster in denser mediums. But 331 meters per second always our sound speed in air or at STP. So sound is a mechanical wave. Mechanical waves are longitudinal waves in that they do not require a medium to travel. Sound cannot travel in a vacuum, so that's why there is absolutely no sound in space. All transverse waves have the ability to travel in space, but when we're talking about sound, sound needs a medium, and air is a medium. Even though we can't actually see it, air is made up of little molecules, which allows for your sound waves to be able to bounce off as it travels throughout air. So sound must have a medium to travel. Sound intensity is another way of saying volume or loudness. We know that that means amplitude, or how much energy is in your wave, in your sound wave in this case. So when we're talking about sound and we're talking about amplitude, amplitude is directly proportional to how loud your sound is. As we move further and we talk about frequency, well, frequency means how often that wave occurs or how often that cycle occurs in 1 second. So if you're talking really, really fast, that would be a greater frequency rather than extending your words. And if you have like one of those sound machines and you're able to take your voice recording and speed it up, what would happen to your sound? What would happen to the sound that you hear? You should hear that your sound gets much higher in pitch. So frequency is directly proportional to pitch in terms of sound. So we have an electric buzzer placed inside a glass jar and turned on. A vacuum pump is used to remove the air within the jar. What happens? What do you notice? Well, if you're inside of a jar and all of a sudden you take out all of that air, well, now you're in what we call a vacuum, where there's no medium inside. So if you do not have any sound, any air, you no longer will be able to hear the sound that's inside. You still would be able to see the electric buzzer like moving around if it did move, but you would not be able to hear it. So now we get into something called the Doppler effect. And like I said, you've definitely experienced the Doppler effect before. The Doppler effect, as you can see, relates to trains or ambulances or a car horn as you're sitting outside on the street or something like that. So the Doppler effect is when sources transmit waves in all directions. They do this with speed, wavelength, and frequency. We already know that. That's everything that we've been talking about up until this point. When a source or an observer move relative, meaning in respect to one another, there is an apparent change in frequency of the source. So there's an apparent change, meaning that the change doesn't actually happen. It's just what you experience at that moment a change in the frequency or the pitch of the source. So, as you have a train, have you ever been sitting outside waiting for a train, like at train tracks, and you try to like guess which way the train is coming based off of the sound that you hear? And then as the train gets closer to you, the amplitude or the energy emitted should become louder and greater, such that the sound is much louder. And then as it passes you, then all of a sudden it starts to decrease the sound. That's the Doppler effect. This effect depends on the relative motion of the observer and the source. So it all depends on the speed and the location of where the source is in respect to where the observer is. As you can see, you have these waves, these spherical waves that are keep popping up here. If you look where the horn is on the train, you see that those waves are closer together, the lines are closer together. Whereas if you look behind towards the back of the train, you see how those waves start to spread apart. So it's much louder, or the wavelength is much shorter, meaning the frequency is greater, closer to the horn, and the frequency then is smaller, and the wavelength is bigger as you move towards the back of the train. So when we talk about relative motion, again, this has to do with your reference and your reference frame. So meaning that if you're in the same frame of reference, meaning that if you are in a car with a horn or in a train with the horn in the front, wherever you are, whatever situation you want to say. So for me, I'm in a car and I'm sitting next to the horn. So I'm in the same exact location as this horn. I'm in the same reference frame. Here in this example, you have the source and observer moving closer. So now you're outside and you're waiting for a train to come near you. Well, then you and the source, are not in the same location. So the observer is moving towards you. The frequency increases, the pitch gets louder, the wavelength gets shorter, because we know that V equals lambda times frequency. Frequency and wavelength are inversely related. Once the source and the observer are moving farther apart, meaning that the observer is moving away from your source. So I'm outside of a train and all of a sudden the train moves away from me. I hear that the pitch gets lower, which means that the wavelength gets larger, because again, frequency and wavelength are inversely related.